All right. If it is sliding to the right, oh no, and it slides to a halt. Okay, so notice right away we're getting suvat stuff there. I see three suvat quantities. Do you see them? Halt and 12 meters, right? So there's really two types of these things. One is suvat, then F equals MA. The other is F equals MA, then suvat. This one is solidly in the category of suvat first. I know that because I've got 1, 2, 3 quantities. It's solvable. If you can do suvat first, do suvat first. Don't sit around wondering whether you should, right? Okay. Okay, so let's see. Sliding to the right, it's already doing that. So that is our initial velocity. Final is 0. This is going to be a negative acceleration. Our displacement is 12 meters to the right, so 12.0. I'm going to choose no t, so 0 squared equals 7.2 squared plus 2 times a times 12. Okay, so let's see. Parentheses, okay, parentheses 0 squared minus 7.2 squared divided by 2 divided by 12. Negative 2.16. Now, when you're doing these problems, I mean, first, don't forget how to do suvat, right? Don't do something terribly unclever like, oh, it's 7.2 divided by 12, right? No, it's not. Use an actual formula, right? So concept 0, just do suvat the way you've always done suvat, right? Second of all, you're still wrong if you miss the minus sign. You can have the right number, but if you miss the minus sign, that's super important. So think about this. It's sliding to the right and it stops. That means it's a negative acceleration. So even if you somehow mess up the signs here and get a positive acceleration, keep in mind it's negative. Okay, so we're going to use that guy, right? So here we are. Let's draw a picture of it. Whoa. Here's our block. Sliding, it's sliding to the right. Okay, it's 5 kilograms. That's supposed to say kg, right? Okay, and there's some unknown force acting on. So let's draw this. F, right? And then, of course, if it's sliding to the right, the friction force is to the left. So 8.3385. We got that in the first part of the problem, right? That guy's going to be negative. The unknown force, all our unknown forces are always positive. And the acceleration is this, negative 2.16. So our expression looks like this, negative 8.3385 plus F is 5.00 times negative 2.16. Now, you miss that minus sign, it's all over. All this hard work. You're back on a Tuesday afternoon. Okay, here we go. To get that, I'm going to go 5 times this. So 5 times negative 2.16. And I'm going to add this. I'm going to go plus 8.3385. I get negative 2.46. Roughly, it's 2.4615, right? Now, that's weird, right? It's sliding to the right and stopping, and I still have to exert a force to the left, right? I'm exerting a force to the left on it to make it stop, right? So, you can stop right now, but I'm going to explain something very important and fundamentally helpful, okay? If you think about this thing, this block sliding along, if the friction force is the only force acting on it as it slides, right? The question is, what is its sort of natural rate of deceleration due to just the dynamic friction, right? Well, let's do that, right? This is just the only force acting horizontally. If it's sliding to the right, is this guy to the left. Okay, so that got to be negative, and our only force is negative 8.3385. Okay? And then that equals 5.00 times some a, right? So let's figure out what our a is here. Negative 8.3385 divided by 5. Negative 1.6677 meters per second squared. So that is our sort of what it would decelerate at if just friction's acting on it. Okay. Now, think about the one example here that we just solved in F, right, is that we got this thing was decelerating. Its rate of deceleration was negative 2.16 meters per second squared, if you recall. Okay. In this example, that's decelerating more quickly than it would with this, right? So that's why that force, that 2.46, had to be this way, right? That's why it had to be that way, because to make it decelerate that rapidly, right, it needed help, because without that force, it would decelerate at this rate, which is a slower rate. The second thing is think back to the problem before that, where we had an acceleration of negative 0.950 or something like that, or was it 920? I can't remember. Okay, well, that's not fast enough. It would decelerate this rate without a force acting on it. That's the rate at which it was decelerating. That's why we had a positive force, right? That's why this force was positive, was to keep it from decelerating at this rate and only decelerated at that rate. So that's a cool thing, right? If you figure that out, you can sort of have a double check, right? And then the final thing I'll leave you with is that this thing is actually mass independent, right? If you recall that, if we write this as a formula, right, that dynamic friction was negative mu times m times g, and then that equals ma. Notice that the masses cancel, which is a very interesting thing. It states that any block with the same coefficient of friction will decelerate at the same rate, or accelerate at the same rate. So I don't know, you have to think about that. Think about what that means, right? Cars with the same tires that are peeling out will accelerate, assuming that they've got the the same weight distribution on the wheels, right? They'll accelerate at the same rate as any other car if the tires are the same, right? And you know all these other things, right? And you're spinning, et cetera, et cetera. That's kind of cool, huh?